everybody an intro of what we're going to have today. We have two lecturers today. First of all, the topic is empirical studies of free will. That's kind of the most direct, or perhaps one of the most direct experimental exploration of the existence or the non-existence of free will. And Ariel will start. Will give the first part of the lecture today. And we are fortunate to have among us Liad Mudrik, Professor Liad Mudrik from Tel Aviv University. And as in the case of Ariel, Liad is also, that's part of her research. And she'll tell us in the second part of the lecture today, her perspective and her findings and her perspective on this problem. So I am one of your students today. So we'll start with Ariel, please.
Okay, thank you. We will, as we said, we'll start with empirical studies. So one of the moments of one of the beginning moments of these empirical studies was Benjamin Libet's experiments about 35 years ago. So we'll get into those experiments. Those experiments created a big, a lot of activity around and a lot of discussion around these issues of measuring free will and of the question, is free will is scientific? Could we do it? Could we prove scientifically that free will doesn't exist or does exist? And some things that were of the domain of philosophy suddenly became part of the domain of science. So in order to go into his experiment, wait. You see the slides?
Yeah, I see them. Yeah.
Okay. So let's say a few words about the EEG. The EEG is measured by putting electrodes over the scalp, and it measures the electrical potential over the scalp. So one of the methods of analysis is called ERP, event-related potential, and ERPs are basically measuring the EEG while having an event occurring during the measurement. The event could be something, some kind of perception that someone sees or hears, or some kind of activity of response that someone does. And what you do basically when you want to measure this ERP is that you have the EEG signal, and it's recorded continuously. However, once in a while, according to the experimental paradigm, you have some kind of event, let's say some tone or something, and then you take the part of, and the event repeats itself and during the experiment a few times. And the reason we do that with repetitive events is because the EEG is a very noisy signal. And now after we have these events, we cut the EEG around the event, and we take these pieces of EEG and we average them by locking them to the event. And then suddenly we see the noise cancels itself, and suddenly we see the signal that we were interested in, or that we discover through this averaging. Okay, so this is the method of ERPs, event-related potential, and this method is one that was used by Libet. So it was discovered in the 60s, 1960s, that before someone presses a button or moves the hand voluntarily, there is and you do this event many times of moving the hand voluntarily, and then you take the EEG and you average it over this, and you lock it to this event of the movement of the hand. Suddenly you discover that if you measure in an electrode on the top of the scalp over the motor areas, you measure even one electrode, what you discover is that you have this ramping up of a signal towards the event. The event of moving the hand or pressing the button is at 0. And what you have here is what they called at the time readiness potential. And it starts about a second or two before the button press or before the movement of the hand. So this was understood at the time. It wasn't 100% clear, but it was kind of pretty much understood that this is a brain activity which is preparing the movement of this voluntary movement. I mean, how do you do a voluntary movement? You tell the participant that's sitting in the experiment room, whenever you feel like it, press the button. He sits and then he feels like it and he presses the button. And then again, once in a while, and then you discover that a second or two before there's this movement. Of course, this type of voluntary movement with this readiness potential will not appear if suddenly someone throws a ball to me and I catch the ball. Of course, a second or two before, it won't be anything because I'm reacting to someone who threw the ball and then I moved my hand. But if the situation is such that that there's nothing interrupting and I'm sitting and voluntarily I could move my hand, then you'll see this type of readiness potential. So Liad took this signal, and in the 80s, he added another element to this signal. So you have a participant on the left picture sitting, and he's instructed to press the button whenever he wants, and he has EEG connected to him. However, he has another element here, which is a clock which moves in a certain speed, not a regular clock, and this clock, he has to notice when the urge to press the button or when the will to press the button appeared in him. Okay, so there's a button press in the end, then he presses the button, but at some point he's aware that he wants to press the button, and he has to note that moment of awareness of wanting to press the button, and then he presses the button, and then he goes and tells the experimenter that where the position of the clock was when he wanted to press the button. Okay, so there's this wanting to press the button, which Liad called in his paper W for will, and there's a button press. And as we saw before, we also have the brain activity, the readiness potential, which prepares for the button press. And what he discovered was the following, that if 0 here is the moment of movement, so of course before the movement, as we saw, there's the readiness potential. However, the will to move or the urge to move or this W appears before the movement, but after the readiness potential onset, meaning that in a way, the readiness potential or the brain activity started before the person wanted to press the button. Okay, so this was the discovery or the surprising discovery of Liad, which, as I said, as a consequence of there were a lot of discussions about this. We'll go a little deeper into this soon. I just want to note a few extensions to this experiment. One expansion was the experiment of Liad that we're talking about is pressing a button whenever you want. So a person has to feel an urge to press now at a certain point. So the question is, what time is he pressing, the timing of the button pressing. However, you could also do other kinds of experiments of what hand are you going to press? I'm going to press with my left hand or with my right hand. I could decide, I could tell a person, okay, choose freely what you want to press with your left hand or right hand. And I could, of course, do both. I could tell them, decide whenever you want to press and decide what hand you want to press, the left or the right. So for the left and the right, you have a what's called a EEG measurement, which we'll go a little deeper into it later, which is called the lateralized readiness potential. Because what they discovered was that the readiness potential, about 200 milliseconds before the button press, becomes lateralized to one of the sides, to the left side or to the right side, contralateral to the hand that's pressing. So if a person presses with his right hand, so there will start becoming about 200 milliseconds before the button press, a larger negativity on his contralateral hemisphere, which is the left hemisphere. So that way they could measure which hand is moving. So which hand is going to move. So that's the lateralized readiness potential, and that was also measured in these type of Liad experiments. Okay, another expansion was even earlier predictions. Here, what we saw in Liad's experiment, that there, I don't know if you noticed the timing, but the W appeared. Let's go back 1 second to the timing. The W, the readiness potential starts about 1 second before the movement onset, and the W appears a few hundred milliseconds before the movement onset. So there is a difference of about a half a second or even more between the brain activity, the readiness potential, the onset of the readiness potential, and the will to move. Okay, so there's half a second. But here, they found through doing a similar experiment, but this time with fMRI, not with EEG, that a person had to decide when to press and what hand to press. So there were the two decisions he had to make, and they, through fMRI decoding, they found what areas decode the movement itself, if it's left or right, and what areas decode the timing of the response. And what's nice about these results is that it takes the brain activity much farther back. It's 8 seconds or 6 seconds before the movement. There's some information in the brain that, and it's significant information that tells you if you'll press left or right. There's a lot of questions regarding this experiment. It's significant, however, very small significance. And but I won't go into it. I just want to show here. I just wanted to show what type of experiments were done afterwards as a result of Liad's results. And these experiments were expanded in time and in type and etc. So basically, we go back to our timeline. So what was Liad's discovery? So first of all, I guess what he thought before he did the experiment was that first you have what's the W, let's call it the conscious intention, because that's the moment that you're conscious of your intention to move. Okay, it's a more exact term, conscious intention. So first you'll have a conscious intention to move, then will appear the brain activity. Then you'll start the brain activity by wanting to move, and then there'll be the movement. I guess that's what he thought before he did the experiment. However, he discovered that it works the other way around, that first there's the brain activity onset, the readiness potential, the RP. After that, the person is conscious of wanting to move, conscious intention, and then there's the movement. one thing that comes up here very clearly is that his definition of the will, if you come and say, this proves that or shows that people don't have free will in a certain way because basically the brain decided what to do. It wasn't the person that decided willingly to press and then the brain started its activity, but the brain started its activity and then the person has some kind of a feeling of wanting to move. So what you see, first of all, here is very clearly is that he understood the will as something that has to be conscious. I mean, talking about intentions without consciousness or of will without consciousness, I guess didn't make much sense to him. So these results were taken to show that here science shows that there is no free will. And soon we'll talk about the criticism about this. But this was at least in the popular view, some kind of big result in this direction. I want to note another thing is that his terminology and language wasn't very exact. He wanted to talk about will, but sometimes he talked about this conscious intention he described as the urge to flex or wanting or the decision to flex, to move the hand, or the will or the wish, all kinds of things, all kinds of terms that if you do some kind of analysis, maybe they are different from each other. Okay, but however, this was the result and people took it to mean that there is no, I mean, I'm saying it very superficial, but that there is no free will. However, Liad himself did believe in free will and he tried to save the free will. So his way to do it was by saying that after you become conscious of your intention to move, there's basically still a window of opportunity to veto the movement. Okay, so the movement started because the brain said, okay, now I want to move my hand. Now it starts preparing the movement of the hand. Then at some point you become conscious of your wanting to move your hand, and that's the will. But then Liad says, then you still, with the moment you become conscious, you could stop you could put a veto on the movement and stop the movement. And the terminology was that he didn't believe in free will, but he believed in free won't. So that is what he thought is how things work. But he didn't really prove this conscious veto, which is very hard to prove in EEG, especially according to what I told you, that when you if you want to measure some kind of signal in this ERP method, you have to find an event which you lock the averaging to that event. But if you vetoed your movement, so there's actually no movement, there's no event that happened. So basically there's a methodological problem. What do you lock? How do you lock your EEG to what? Nothing basically happens. And that created the problem to measure. I mean, at least in this simple, I mean, in his methods, the veto. So that was one problem. Another problem with the veto was in trying to tell people, okay, press whenever you want, but sometimes veto the button pressing. That of course creates a question: did they ever want to press, or did the veto from the beginning? Was the plan maybe the veto was they had in mind from the start? Are there any questions?
Yeah. I think you could argue that this was a trigger decision. I mean, that you made the decision to move in the beginning of the experiment and then just waited for a specific trigger. So it's not actually a decision at all at that point. Yeah,
that's a good point. That is one of the criticisms. I didn't bring it here, but that is raised regarding to this type of decision. It has to, that people basically, their decision is in the beginning of the experiment, where they decide, I will start the experiment, and at certain random times, I will make the movement. So basically, the intention isn't in each movement and movement, but is a general kind of intention, which is in the beginning of the movement. Yeah.
But the timing. But for this, because of the issue of locking, the question is whether also at the beginning, 2 seconds beforehand, there was already an intention to move at that 2 seconds or whatever ahead. It's not enough if you just have a general intention.
No, it's true. You have the readiness potential is specific for each movement and movement. That's true.
Yeah. So I'm not sure what would be a plausible story that you have 2 seconds already decided that I'm going to move 2 seconds in 2 seconds, and then I forgot about it, and then a few hundred milliseconds I say, I decided, so now I'm going to move. I don't know. Yishai, what would be the scenario? I don't understand.
Well, maybe you decided on some kind of trigger. Maybe it wasn't like a very well-defined decision, but it was enough to create some sort of, a spring that's winding down. And then at some point, it just triggers.
So that will be related to what we'll talk soon about.
Okay, that's something else. Okay.
Yeah. So
can I also ask a question?
Later. Ken? Yeah?
How, it just sounds to me like a very not precise kind of nisui. Is that the word?
Experiment, yeah.
Experiment, yeah, because you need to trust the participant to be like, oh yeah, that's when I decided at this time. And it seems to me like it's a very not, I don't know if you can really trust that kind of information.
Yeah, very good point. I mean, I'm bringing the experiment soon. I'll come to the criticisms. I think you're going to say them all if I leave the. You're right. That will be our first point. But before I get to that, I want another subtle issue is the following. What do we have here? Basically, this is the timing of, we have first readiness potential, and then we have conscious intention, and in the end we have movement. However, this timing could be explained according to two pictures. One will be a causal chain picture, which we have readiness potential. At some point, we have to have the conscious intention as a causal link to reach the movement in these type of actions. The other way to understand it would be that you have the readiness potential, which leads to two different, let's say it this way, leads causally to the movement. However, it has another link, which is to this conscious intention, which we would call in this case an epiphenomenon. I mean, it's not part of the causal chain itself, but it's some kind of addition which comes together, accompanies this type of movements. And whoever said it, Daniel Wegner said this nicely. The position of conscious will means our conscious intention in timeline suggests perhaps that the experience of will is a link in a causal chain leading to action, but in fact, it might not even be that. It might just be a loose end, one of those things like the action that is caused by prior brain and mental events. And in a way, so so even though you find the timing, the temporal order, the way Liad found, you still have two ways of explaining it, either as a part of a causal chain or a part of some kind of epiphenomenon. Okay, so now let's come to the critiques. So this was the experiment. Now let's look at a few criticisms we have about it. So the first thing will be the W timing, which we call the conscious intention timing, which May already brought up. The second thing will be notion of picking versus choosing, which I'll just mention, but Liad will mainly talk about this aspect. And the third critique was maybe the readiness potential. The RP is not actually a readiness potential. So let's go one by one and see what we have to say. So regarding the W timing, so first of all, before I go into this figure, as was mentioned here, it's a very difficult thing to measure. What are we measuring exactly? What is this W time? What am I looking for as a participant in such an experiment? Where is this W when I'm doing the experiment? Do I feel anything when I'm told to press whenever you want a button? I don't. Try it by yourself. I'm not sure you'll feel any will, any intention, anything. You'll just do it. But people do feel something and do report something. So what's interesting is that what is this W? So first of all, conceptually, you should realize that if we're talking about this conscious intention that we have, which is the W, again, I'm using a little different terminology, but this conscious intention, which is reported by me, which I'm trying to become aware of when my conscious intention was, and that is the W. So the W is my report of the conscious intention, meaning that conceptually there is something that's called conscious intention, which happened in a certain time, but was maybe my report about it is a little mistaken or not exact, etc. But there is a time which is called the conscious intention, and I could try to figure out how could I find out what that timing is. Maybe reporting isn't a good method. Maybe there's a different way of finding. And there were experiments done to try to find in different methodologies what is this moment of conscious intention. But here we have an experiment, which was a nice experiment, very simple, which people did the Liad experiment. However, after they pressed the button, there was a beep, a feedback. There was this feedback beep, which they heard. So they press the button and they hear beep, beep whenever they press the button. However, the manipulation which was done here is that the feedback was sometimes exactly when the beep was, but was also moved forward in time. So you press the button and like 5 seconds afterwards appeared, 5 milliseconds afterward appeared the beep, or 10 milliseconds, 20, 30. And so there was this little lag of the feedback between the real moment where you pressed and when you heard the beep. And what they found is that what the x-axis is this lag, this delay of this beep response, and the y-axis is the timing from the movement. So what they saw is that, I mean, the higher numbers in the y-axis means that your report of W is earlier in time. So let's say when they had a delay of 5 milliseconds of the beep, so the person reported that the W was 120 milliseconds before the movement. And as the beeps went forward in time, the feedback went forward, then you see how the W reports go forward. That means that actually we kind of infer when W is. We don't really have in mind the exact moment of W and know how to probe it, but we infer it from things that happened in this context. So one of the things that happens is when I press a button and I infer when was the W, and my button pressing is a dependent or I think so. It's dependent on this feedback. Okay, so that's the W timing. There's a lot of issues around the W, on this aspect of W, but I want to go on. Okay. So the next point is the point of picking versus choosing. This terminology was given in a paper by Edna Ullman Margalit and Morgan Besser, a philosophy paper that differentiates between two types of selections we do in free choice. We have selections in which are meaningful, and which I have to decide between two options that have some meaning between them, and I have reasons why to choose one or why to choose the other. Those are called choosing type selections. However, we have selections which are picking, and those are selections in which I have to do a selection. I have to pick something, but I don't care what I'm picking. I mean, there is no reason why to pick one and not the other, or there's no consequence to why to pick one and not the other. And so there's some kind of symmetry here, and I don't, which I don't care about. So, but I still need to do a selection. So that's picking. So Liad will talk more about it. I just want to touch upon the aspect of picking, and think about what happens in picking. So one of the criticisms, we're talking about the criticism, one of the criticisms about the Liad experiment is that it deals with cases which are picking cases. Because what am I told? Choose a moment in time, or choose what hand you want to press, or things of that type, which I don't care about. I don't care what moment in time I'm picking, and I don't care which hand I'm pressing. But I have to do a selection here. So this was one of the issues of the criticisms against Liad, that all the types that he's talking about, the experiments are picking type experiments. But I want actually to focus on these picking type experiments. So philosophers dealt with the issue of picking, or of symmetry between options, and we have a few opinions. So we have a Spinoza saying that actually, if someone will be in a certain situation in which he has to pick between two symmetrical options, he will actually be paralyzed, because it's symmetrical and he can't decide what to pick A or to pick B. And if his life is dependent on it, it's even worse, because then he will actually die. I mean, if he's very, very thirsty and there's two cans of Coke, but they're symmetrically far from him, so he can't pick any, and then he will die. Okay, so that's Spinoza's view. Newton, we met him in different contexts, but he also talked about free will, claims that no, actually, when people are doing the picking, that's when people use their agency and their free will. So free will is something that is brought in, especially in cases which are symmetrical and where things seem not the same. This he wrote to a letter to Leibniz, and Leibniz replied to him, and Leibniz basically agrees with Spinoza that in a case of symmetry, there is no decision. You can't decide what to do in a picking case. However, Leibniz claimed there is always a difference. There's never real symmetry between in a certain situation. And Leibniz says there's always a minute kind of difference, or some kind of perception that you're not aware of, that makes a difference, that creates this difference. Okay, so now we're talking about Liad experiments, which are picking experiments, and we see that there is picking done here. So the question is, what happens in a picking situation. How is the selection done? So although on a reason-based level, there's symmetry between the alternatives, on a relevant neuronal level, there must be some asymmetry breaking the tie between the, I mean, if the options are two options, or if the timing is if we're talking about what time to move the hand, or which hand to move. So there's some asymmetry that decides it. And the source of this neuronal asymmetry could be either, like Leibniz says, a kind of external subliminal bias, that there's always a difference because there's something external, or a kind of an internal bias. Internal bias could be either something within you that creates a difference, or a kind of what we would call a neuronal random noise, which would create some kind of fluctuation in one direction or the other, and that would decide what would happen in this type of picking situation. And that brings me to the third critique, that maybe the RP is actually not a readiness potential at all. So this brings us back to what we've talked about in the lecture number 4, when we were talking about decision making, and we were talking about accumulating evidence within a process of integration to a bound, to a kind of a threshold, which there the decision is made, and things start moving. We called it the drift diffusion model for decision making. And what we showed is that the evidence, which is the time we were talking about moving dots, if they're moving to the left or to the right, but it's a perceptual kind of evidence. It accumulates in one direction or the other until it crosses a threshold, and that's the decision which is made. However, this same idea could be used also here, where you don't really have any external evidence. What you have is these fluctuations of neuronal noise which fluctuate, and when they cross one bound or the other, that would be the decision that is made. Meaning that when information for a certain decision is weak or ambiguous, if there isn't a strong bias which is clear, which is to one direction or the other, the threshold crossing is mainly determined by subthreshold neuronal noise. And this was a claim by a paper by Scherger, 2012, which actually took this idea one step further and said, you know what, this idea of the readiness potential is basically nothing but just neuronal noise reaching to a threshold, to a bound. And what we basically see is the following, that, I mean, people have to decide when to press the button. So what do? They sit around until the fluctuations reach in a certain area, reach this threshold. It reaches the threshold, and then the movement starts. Okay, so sometimes it reaches the threshold pretty fast. The fluctuations become closer to the threshold. Sometimes it takes longer till it reaches the threshold. In any case, at certain points, it reaches the threshold, and then there's a movement. And now what they claimed in the article is that the readiness potential that we see is basically an average of all these subthreshold neuronal noise signals that cross the threshold. So if you look at it that way, so basically what we're talking about here is not readiness potential, is not a readiness potential in meaning that it's preparing the movement. What we see is an average of this brain activity which could have happened and not reached the threshold. But what we take is all the cases where it reaches a threshold, and then we average locked we lock it to the movement, meaning we lock it to the moment where it crosses the threshold, and locking it to that moment will give you the shape of the readiness potential. So basically, RP as a stochastic threshold crossing means that RP does not reflect readiness or preparation. And another thing which they noted is that the W time is actually very close to the threshold crossing. So in a way, maybe this consciousness aspect is the moment which the threshold is crossed, and then I become conscious to this movement. But I'm not becoming conscious to a decision which was made 2 seconds before, and now I just become conscious to it. And what was before was just brain activity with no decision. Now I'm becoming conscious at the moment of the decision.
Ariel, can I interfere for just a second? Just because it will also be crucial for what I'm going to present. Aaron gives an excellent metaphor, which I think helps very much to understand the point. So if you can go back to the figure of any readiness potential, not before even this one, just was some readiness potential, you probably had many of those here.
Only in the beginning.
Yeah, okay, so I'm okay. Yeah, this one. So typically what people assume is that when the readiness potential starts to rise, let's say here about 2 seconds prior to movement, this is actually the onset of some unconscious decision that initiated or instigated a process that would later on lead to movement. So what we know, the fact that the readiness potential starts a second or half a second or 2 seconds before movement onset is taken as evidence for some internal unconscious decision that took place and then led to the movement itself. But what Aaron's model shows is that we can get the very same pattern of activation just by, like Ariel very nicely explained, just by averaging over completely stochastic patterns of like random fluctuations that by chance sometimes cross a threshold, and this leads to movement. And the important thing is that here the onset of this accumulated signal means nothing. If you now go back to the figure from Aaron, the only thing that this onset signals is just the long the long trials where it took these fluctuations longer to cross the threshold. And the metaphor that I wanted to quote, Aaron's metaphor, is that it actually becomes it's timely. So he usually uses it with the flu, but let's use it with COVID, okay? So I don't know actually if it works with COVID. So let's use it with the flu, okay? So you could, in principle, track my immune system over time. And then, or you can do that for many, many people. And then you can ask, what are the relations between the state of your immune system and getting infected with the flu? And if we do that, let's say that we track my immune system and Ariel's immune system, and then we lock all the signals to the onset of a flu, to the time when I actually became ill. Then what you would see is like a decrease towards my getting ill, a decrease in my immune system. And why is that? So as Aaron explains, your immune system, just like these random fluctuations, is fluctuating between being very strong and being relatively weak. So for example, today I'm at the end of a week where I slept very little. So my immune system is probably in a pretty bad shape. I didn't sleep well, I didn't eat well. And then I meet someone and that someone is ill. And then I get in touch with the virus. And then I also become ill because my immune system is not strong enough to fight it. But let's say that I met the very same person when I had a very strong immune system, then I just wouldn't get ill And the researchers wouldn't know about it. And because they only lock the signal to the time where I actually got ill, it makes sense that my immune system on average would be lower in these cases, because it randomly fluctuates and it only crosses the threshold. I only get sick when it's low. Similarly here, these fluctuations just randomly, go up and down, and we only lock the signal to the time of the movement where these fluctuations were at their peak because they crossed the threshold. And sometimes it took longer, sometimes it took faster. When you average everything out, you would get something that looks like a genuine brain signal, but is actually not such a brain signal. And the onset, and most importantly, the onset of that signal does not index some kind of an internal process, because it's just the tail that is caused by the long trials. So I think this is the critical point. Now, what Aaron's work shows is not that the readiness potential is the result of random fluctuations. It just shows us that it could be, that it is compatible with a model where there is no signal and there is only noise. So I'm sorry for interrupting, but I just wanted, I always find that this flu kind of metaphor helps understanding the crux of Aaron's work. So
may I add to this explanation of the RP and the flu? What I think is, at least to me, to my ear, was missing from both of yours description is the assumption, not assumption, we know, of presence of correlations. If the signal was uncorrelated in time, or let's say correlations of let's say 10 milliseconds or 20 milliseconds,
excellent point,
or 50 milliseconds, then this explanation will not hold.
Yes.
The fact that it's going backward for 2 or 1 or 2 seconds is not because sometimes it takes long. I don't think that's the explanation. The explanation is that the correlation, the temporal correlation of these fluctuations have the time scale of, I don't know, half a second or so, or at least of that order. Okay. So basically what in this, according to this explanation, the RP rise is basically a reflection of temporally correlated fluctuations. It will not hold this explanation if this was fluctuations with a very short correlation time.
Yeah, I think the critical point here, I strongly agree, is the fact that we have a biased way to look at the signal because we only look at the action onset. So we lock it to the action onset. It wouldn't have happened if we could have also looked at events without an action. And
that's true.
And the autocorrelation of the signal.
Right.
I agree.
Right.
Yeah.
I agree.
Yeah.
I also want, I don't know if Liad, if you'll talk about it, or Ariel, I don't know if this is now time the discussion, Ariel, or you.
Yeah, it's a good time.
So I think this is a very nice explanation, or potential explanation, as Liad said, of the readiness potential. It's not really readiness, but and so on. But it's not. It does not reflect directly on the question of Liad or the will issue, right? Because basically you are saying that the mechanism, this unconscious mechanism that generates movement is not some internal unconscious signal that decides, but it is the random fluctuations. But also with random fluctuations, you don't have, it doesn't explain what is the role, what is the role of the will time or the willing or the urge.
Ariel, do you want to answer?
No, I'll just say a few things. Just the aspect of there's two issues here. One is that that you would say, okay, this is a picking situation, and a picky situation. This is what this would be a good mechanism for me to work with.
That's good. Okay.
That's it. And the other aspect is just really doesn't answer, but it's just the issue of the W. Where's the W? I mean, from the moment of decision. So if the moment of decision is the onset of the readiness potential, then the W is much later. And if it's together, then W reflects at least that moment. But it still doesn't create the opposite. First you will, and then you start the movement. I mean, it just.
So basically, what you are saying is that this is just maybe a mathematical way to establish the irrelevance of free will in a picking situation. Basically, that's the way I interpret it. But maybe Liad, you want to say something else?
Yeah, so I think, first of all, I fully agree with Ariel. It says that maybe meaningless decisions are indeed determined by some noise or symmetry breaking mechanism, and I think most of us wouldn't have a problem with that. But I think more importantly is that what the sugar work shows. So the entire problem stems from the fact that we seem to have evidence for neural activity preceding conscious decision. Now I will, set aside there is a metaphysical question here or a philosophical question here. The way I think about it, conscious experiences will always be preceded by neural activity because something has to give rise to the conscious experience. So in my opinion, the Libet argument to begin with is problematic because it's simply dualistic. It kind of assumes that conscious experiences come from thin air, which I don't think is the case. But let's take the argument as is and say, okay, but this neural activity is not related to the conscious will. It's related to the motor preparation, and then we have a problem. What Aaron shows is that this evidence simply might not index an earlier onset of neural decision to move, of motor preparation to move. Because if we cannot treat the onset of the readiness potential as an index for an unconscious decision, it could just be an artifact of the way we measure the signal, then we don't have this discrepancy and we just don't know what the relations are between the conscious experience and the neural activity.
I beg to differ.
Okay.
Because following my statement about correlations, it's not an artifact. It's not a readiness in the sense, the Germanic sense of readiness. But the fact that at a given time, statistically speaking, the signal crossed the threshold at a given time is most likely, because of the correlation, is that the signal was large, was high, relatively high relative to the mean, 2 seconds before. That's what it means, temporal correlation. And that is the event that decided that I'm going to move it 2 seconds ahead.
No, but the question,
so it's still causal.
So
it's still causal.
I think the question is, if you accept the interpretation, the model, if you accept the model, again, maybe I'm misunderstanding.
No, I'm accepting the model that it's not a readiness potential, it's fluctuations of noise. But it's fluctuations of temporally correlated noise, which means statistically that if the signal was reaching a threshold at a given time, then statistically speaking, the signal was likely to be high already 2 seconds before. So that was already the information in the brain probabilistically that I'm going to move 1 second or 2 seconds ahead.
Yeah, but I think the critical point here is that, so I completely agree, but I just think that the critical point is how do we interpret, where can we say that the process, may it be a decision or random fluctuation, began? If we
correlation time. That's a statistic.
But so Ariel, I'm sorry that I keep moving you between slides. But if we go to the readiness potential itself, the way do you want to just to show the readiness potential just for a second? The way I understand it, and I will just annotate over your slide if that's okay. The way I understand Aaron's model, and I might be wrong, is that So this is the time. Can you all see my my drawing?
Yeah.
So this is the time where the threshold was set, right?
Okay.
And the reason that we have here it's higher than here is that here there was a trial where very quickly, giving the model very quickly, the threshold was set. And like here, this is, so let me explain differently. Here, this is the longest kind of trial, this one, from this point, this is the longest trial where it took the random fluctuations to cross a threshold. And this is a shorter trial, and this is a shorter trial, and more and more and more. And here we have a very high point because here all the trials were high in the fluctuations. And here we have this is a short, we have less and less long trials, which is why this amplitude is lower and this one is higher, because this is an average of all the model runs.
No. I think it's wrong.
Okay, so how do you explain?
It's simply take temporally correlated noise. It's very simple experiment to do in MATLAB, and this will be a homework, a good homework. Take a temporally correlated noise and put a threshold. Okay. Then statistically, if the correlation time is tau, then the signal will be high tau times beforehand. That's all.
No,
There's
but if you
nothing
go back,
more than that.
Yeah, if you go back to Aaron's model, and that's the last time I move it between these two slides, then you can see that what he shows, at least the way I understand it, again, I might be wrong, but here, so you see, you have all the runs of the model.
Yeah.
Each line here is a run. All of them cross the threshold here. And then what you do when you average all those trials is you take all the arrows to one point, right? This is where the threshold is.
That's the same thing. It's not different from what I say. It just the add that it doesn't show you what happens at zero. But you should have run it -5, and you'll see there's nothing special.
No, but I think I think what happens is that because you have short runs, and here you have longer runs, and here longer runs, and so on.
No, it's not. It's not short because you decided to compute from zero.
Exactly, but
arbitrarily. As a result, there's nothing. It's arbitrary.
No, because this is trial. So he says this is move closer to threshold. So the idea is that in these trials, subjects moved faster than in these trials. This is a long trial, and this is a short trial. You see, so that, but because we average everything to movement onset, this is again how I understand the paper. Because we average everything to movement onset, then the long trials and the short trials, they accumulate. And the reason what we think is the onset of the readiness potential is just the fact that we have fewer longer trials where you have a longer trace. And here everything, like in the movement onset, this is the peak of the noise, the peak of the fluctuation, what have you. Okay, this is where it averages.
Okay, I don't want to spend more time on that.
Okay.
I'll run the MATLAB and show you that it's just a simple correlations of noise, nothing more than that, in my view.
Okay.
Can I ask something? When you say cross the threshold, what sets the threshold?
Ariel, do you want to answer, or should I?
I mean, that's it's a good question, because really that's one of the issues. Okay, how do you create this this threshold? And it might be that if in the instructions they tell me that I have to respond whenever I want, but within 5 seconds each time, or 10 seconds, then the threshold might be I'll set the threshold in a lower position, because I want the fluctuations to cross the threshold within the timing. So the setting of the threshold, I think, is a good question. How is that done?
In that case, the threshold will be W, like the point where you set the threshold.
Again, the
threshold would be the conscious act of will, not the actual whatever comes out.
No, it will be
But
the
you set
onset
the
of
threshold in advance. I mean, when you like start the experiment, like you said before, that you come in with a ready to implement this general intention. So in that implementation, is part of it is setting a threshold. I assume.
Liad, you want to comment on that?
Yeah, to my understanding, like I don't know what in the brain sets the threshold. Like this is a theoretical model, and we can actually play with the distance between the boundaries or to set the threshold and see what happens. And this will be one of the factors that you could play with when you create the threshold. But it would, you can think about the physiological mechanisms that underlie such a, for an action potential, right? You also have a threshold that is being set. Once the cell crosses that threshold, we have an action potential. So I think that it's basically, it's a parameter of the model that we set when we model it, but in the brain is physiologically or biologically implemented, the way I understand it again.
Yeah, I think it's a good question, but I think because of that, Ariel, your earlier comment about symmetry and symmetry breaking and what is the origin of symmetry breaking and so on, I think this kind of symmetry issue makes more sense, or the picking related makes more sense when we talk about deciding to move right or left. But I don't think there is symmetry about time, when to move, because there is obviously the subject is not going to move 100 millisecond, once the trial starts, and he's not going to wait 5 seconds to move, is or 10 seconds. The experimenter tells the subject, look, you choose when to move, but don't fall asleep. So there is an urgency to move at some point. So the threshold may actually not be fixed, but actually may go down slowly with time, because at some point the subject was dreaming about something else, and I forgot to press the button. He will press, or she will press the button. So the symmetry, I agree that when to press a button in such an experiment is not a very meaningful decision. It's not going, it doesn't have moral or practical aspect to it, but on the other hand, it's not really something of symmetry. Mm-hmm. There is no, in this kind of temporal context of a trial, there is no real symmetry.
Yeah,
it's something. It's in between. It's not choosing in the sense that there is some reason or meaningful.
Yeah.
Some reasonable. Some rational debate to move now, to move later on. I agree. It's just. It's really from that perspective. But if you talk about kind of symmetry that you need to break, I think time is naturally something which will not be invariant under these conditions.
Yeah, I could agree with that. I mean, there's some kind of buildup, which, I mean, it's not the same after a few seconds to what it was in the beginning. And I mean, the moment in time, it always considers what happened before. So no moment of time is symmetrical to a moment, to a different moment, because it's sequential. And you're right.
And as you know, well, more sophisticated models of decision making will have a ramping down threshold to actually model, to capture that urge. If you are waiting too long, then you will just make a decision.
Yeah. So that's Isha. You sometimes could have a threshold that, not a straight threshold, but one that descends.
Yeah. We'll basically pick up from where Ariel has stopped. I wonder how far back I should go. Just Okay, so just one word about this picking versus choosing. Let me share the screen. Okay, so Ariel, can you see, wait, can you see my slides?
Yeah.
So Ariel already described the Libet experiment, and maybe we should also say that the same finding was also found in fMRI. Here, 9 seconds before subjects moved, John Dylan Haynes' group was able to predict with some accuracy, not super high, but still significant, whether they are going to move right or left. And Yitzhak Fried with Roy Mukamel and others have shown that even when you look at single neurons, you get this increase in activity or decrease in activity preceding action and W time. And Ariel indeed already said that this gave rise to claims against free will, saying that there is no point in our conscious deliberation, whether, if you're Hamlet, if you want to be or not to be, because at the end of the day, the decision is being made outside of our conscious awareness. It's been made unconsciously before we are aware. And as Ariel rightfully said, at some point in my work with Uri Maoz, who is now at Chapman University and UCLA, back then we were both postdocs in Christoph Koch's lab. Uri, and also, by the way, with Ram Rivlin, who is at the Hebrew University from the law department. We discussed a lot about the difference between picking and choosing following the paper from Unman, Margalit, and Morgenbesser, with picking decisions being unreasoned and typically non-consequential, and choosing decisions being reasoned and consequential. And as Haim said, one kind of even trivial question is to say, well, if all the experiments so far have been using picking paradigms, meaning that the readiness potential has always been documented in the type of paradigms where the decision doesn't make any difference, then it's interesting to ask whether we would find the same finding for choosing decisions that are reason-based. And we should say that when you look at philosophical accounts of free will, especially when it comes to moral responsibility, then people always talk about choosing decisions, about reasoned decisions. And some of the definitions of free will actually say that an action is free only if it is reason responsive. So the place of reasons in our in our attempt to estimate if an action is free or not is very important. But all the neuroscientific studies focusing on the question of the relations between neural activity and conscious experiences of making a decision have focused on picking. So basically we said, instead of asking subjects to decide if they want to be or not to be, which is indeed what we would hope would be a free decision, they're asking them to decide if they want to move or not to move. And we thought that this is not the question. And so what we did was to try and devise a study where we would be able to compare picking versus choosing in the very same paradigm, with as little differences between the conditions as possible. In order to do that, we recruited subjects who were socially involved. So they claimed to be socially involved, volunteered, voted in the elections. This was in the US, so people are less, prone to vote there than they are here. So it's more of a measure. And for each subject, we presented a series of organizations, and they had to rate how much they wanted to donate to that organization. And as you can see here, there are organizations where they are, fairly consensual. So everyone would want to, give money to fight hunger, but there are also organizations that are more controversial. So if you want to give money for, pro-life, you would probably not want to give money to Planned Parenthood. So aside from the consensual ones, we also had more controversial ones in order to get a scale of ratings. And then what we did was, for each participant, we made an experiment in which in every trial, we presented a choice to which organization you would like to donate money. And subjects knew that at the end of the experiment, there will be a lottery. And in that lottery, one trial would be selected. And if that trial is selected, then we would give a real donation of $40 to that organization in your name. And subjects also knew that at the end of the entire experiment, of the entire data collection, we will have a big lottery, and there we will randomly, select one subject. And that subject, if, let's say that Ariel is the subject that won the lottery, then the trial that was selected for Ariel, we would actually donate $1,000 to that organization. So subjects knew that every decision, every choice that they're making in the experiment could potentially lead to a real $1,000 donation under their name to that organization. And I can tell you that I was fairly, I really hoped that, one of the good organizations would be selected, good in my opinion, at least according to my values, which at the end of the day was the case, but it was a bit of a tense moment when we did the lottery. In any case, so we had, in a choosing trial, we had either a hard decision, which was two organizations that have only 1 point difference between them, or we had an easy decision where the two organizations had at least 4 points difference between them. And that was
I'm sorry. Can you say it again? How did you measure it? I missed it.
Yeah, so at the beginning of the experiment, each subject rated each organization on a scale of 1 to 7.
Okay.
Then let's say that you gave the Hunger Project 6 points,
okay.
Whatever, cancer, then we created this trial for you.
Okay.
And if there were 4 points, these were easy decisions. And then we also had the picking condition. So the picking condition was exactly identical to the choosing condition with easy and hard choices. But here, irrespective of what you pressed, whether you pressed right or left, both organizations would get $20 if this trial is selected, or if you are selected, $500. So the idea here was that in each trial, you have the exact same visual input. It's always the same. It's always two organizations. By the way, each trial was unique. So you never saw the same decision twice, besides between choosing and picking. And the motor output was also identical, because you're always pressing right or left. But in the choosing, you're making a reason-based choice that would lead to might lead to an actual donation to an organization, while in the picking condition, you're just randomly pressing right or left, because whatever you press, both organizations that appear on screen would get the same amount of money. So the rationale here was that we have as similar conditions as possible in the two scenarios, but in one case, you are making a choosing, meaningful decision, deliberate decision, and in the other case, you're making a meaningless, picking, arbitrary decision. And our question was, will we find the readiness potential in both conditions? So it was basically a 2x2 design. So just to give you the flavor of the experiment, this is how it looked like. This is a choosing condition. You see two causes on the screen, and you just choose the one for which you would like to donate potentially $1,000. And in the picking condition, you get this notice saying that whatever you do, each of them would get $500. Now, of course, you might say, wait, that's not a fair comparison, because in the choosing condition, you must read what's presented on screen. And in the picking condition, you can just close your eyes, right? You don't care. So in order to control for that, at least to some extent, we also introduced catch trials, like memory probes, that would be a better word, so memory probe, where you will see that in a second, where you're asked which organization appeared in the previous trial. And so that at least forced our subjects to pay attention to the names here. This is a memory trial. So they had to pay attention to the names, they had to read them. Of course, it's still not the same cognitive load, but that's actually inherent to the manipulation. In the deliberate condition, you're making a reasoned decisions. You're thinking about it, you're deliberating. In the arbitrary condition, you're not. So this is how it looked like. We had blocks of deliberate and arbitrary decisions. Each one had 9 decisions, and somewhere in between there was the memory test. Now, the first thing we looked at, of course, was behavior. So we wanted to make sure that the manipulation worked. So what you see here are reaction times and consistency scores. Each dot here is a subject. If the subject is, so every subject did both the arbitrary and the deliberate decisions. So basically each subject here is represented by 2 dots, one for each condition. The x-axis on the left represents reaction times in hard decisions. The y-axis represents reaction times in easy decisions. And so if the point is on the diagonal, of course, it means that the two reaction times are identical, right? If they are below the diagonal, it means that harder decisions were slower. So for example, you cannot see my cursor for some reason, but if you choose one of the dots, let's say the one that almost touches the boundary with 3.5 milliseconds in hard decisions and 2 seconds in easy decisions, right? And the histogram on the bottom part kind of shows you where the dots are with respect to the diagonal. So what you see here in the reaction time plots are two important things. One is that on arbitrary trials, subjects are way faster than on deliberate trials, as you would expect. The other thing that you see here is that on arbitrary trials, they are indeed more or less on the diagonal. There is no difference between easy and hard decisions because the values here are not important. But for the deliberate decisions, you do see that subjects are way slower for harder decisions and then for easy decisions, and they are also slower in general, which is what you expect. Another nice thing that validates our manipulation is when you examine the actual choices that they made during the experiment, how do they kind of relate to the ratings they gave at the beginning of the experiment, right? So how consistent are they? So let's start with the choosing now, with the red condition. So you can see very nicely that when the decision is easy, they are basically around 1. So they always choose the organization they prefer by 4 points or more, which again makes sense. But when it comes to hard decisions, difficult decisions, then they are around 80% consistency. And that also makes sense because, I gave 6 points to the hunger project and 7 points to, fighting cancer. But now when I see them one against another, I say, okay, maybe I actually want to give to the hunger and not to the cancer research organization. When you look at the arbitrary trials, you see that they are way closer to chance, around 50%. But also you can see that for easy decisions, it's still somewhat harder for them to remain completely impartial. So it's still hard for them to choose there. It's not a lot. It's like, I think 55% consistency, but it's not 50%. So they're a bit biased towards their preferences also in the arbitrary decision. But these results made us very certain that the manipulation worked. We had arbitrary decisions and we had deliberate decisions, and they were very well subjects behaved very well according to what we expected them to. So what about the readiness potential? So I'm starting always with showing individual data because I think it's more revealing, and when you collapse everything together, everything always looks nicer. So these are the activations, the EEG as recorded on the CZ electrode, where you expect to find the readiness potential. Each line here represents one subject, and you can see that there is a nice readiness potential for most subjects in this arbitrary condition, replicating the classical Libet finding. What happens in the deliberate condition? Well,
the readiness potential goes downward here. I mean,
yeah. So just because
they go upward, but it's just the same thing. Just
just because we plot negative down. So in the classical readiness potential, they plot negative up. And some still do that actually. And there's kind of there are two traditions in EEG, whether you want to show the negative down or negative up. I think it's more traditional to show negative down, but actually that's considered innovative to do that. Yeah, but the critical thing is that for the deliberate decisions, we get no readiness potential whatsoever. So this is how it looks for individual subjects. I will now show you how it looks. And this is, of course, highly significant, the slope for arbitrary decisions, not for deliberate decisions. And when you look at the data collapsed, so averaged across subjects, you can see a very nice readiness potential in the arbitrary condition with the expected distribution. And you don't see it for the deliberate condition, and also the distribution, like the scalp distribution, is not typical of anything that would resemble. There is some lateralized activation here, which we don't understand, basically. So just to say, if Libet, would have conducted his studies on deliberate decisions, then he wouldn't have received this finding. There wouldn't have been, so many papers claiming that we don't have free will. Now, again, to be very precise, we are not presenting any positive evidence for free will. The only thing that we are showing here is that the most prominent neuroscientific finding against free will, which is the readiness potential, does not generalize into meaningful decisions. So,
Liad, sorry, the blue one is for arbitrary.
yes.
And which one is for deliberate?
The red ones. The red ones are deliberate, easy and hard.
Okay, but the red line do show it's reduced, but
no, they don't. So if you I agree, at the beginning we thought that maybe there is something here, but when you look, both statistically, we used Bayesian analysis and traditional ANOVA and cluster-based permutation analysis, and in none of them does this thing come out. And also linear regression, none of these show that this, what seems to be a bit lower than zero, is significant. And also note that we are not comparing to zero, we are comparing to baseline.
Of course.
And so this this, what seems to be some kind of a decrease here, is actually not significant. It could be that with more subjects it will be, but it's not. So, and let me say that we also tried to look at different explanations and confounds that might have explained this result. So one thing you would say, well, in some trials they responded in the right hand, in some trials they responded with their left hand. Does that result depend on the response? So we tested it for right hand only and left hand only. Still, you don't see anything different in the pattern. We then said, well, maybe it stems from the difference in RT. And that is actually a very important concern, because it could just be that because the choosing trials are longer, then the readiness potential is more smeared somehow. It's less easily kind of averaged because we have more variable and longer reaction times. So in order to account for that, we did two things. One is to divide the subjects by subjects who were fast in the deliberate decisions and subjects who were slow in their arbitrary decisions. So what you see here is when we plot the data only for the fast subject in the deliberate condition and the slow subject in the arbitrary condition, making the reaction times way closer. Still, we get the same pattern. We also tried to see if there is a correlation between the difference in reaction times and the difference in readiness potential between the conditions, and there wasn't any significant correlation. So it seems as if the reaction times might not explain this issue. We then asked maybe the
yeah. Why wouldn't you expect in the hard deliberate case to be to maybe turn basically into a picking situation?
Excellent question. So philosophically speaking, you could say that very difficult decisions, very hard decisions actually amount to picking. Because it's like, Buridan's ass, you are, like Ariel explained before, with, Spinoza and Leibniz, and who was there? Spinoza,
Newton and
Leibniz. Yeah, and Leibniz, as I said, and Newton, thank you, sorry. That indeed, when you are facing a very difficult decision, it's similar to a picking situation. So there are two things I will say about that. A is that we are now running an experiment in the lab led by Yoni Amir, in which we try to see if this is indeed the case. So there is a very famous argument by Jean-Paul Sartre, where he says, if I have to choose if I want to go and fight with the resistance or stay with my ill mother during the Second World War, and you give me like a penny or $1, and you say, well, I say I can't decide because these are two equally important goals. I want to fight the Nazis and I want to stay and take care of my mother. And you say, okay, if they are equally important, then give me just $1 and that should bias the decision. And he says, no, the most difficult decisions, as opposed to picking, cannot be sweetened by a small amount of money. So what we are now doing is to see whether we can apply this logic and identify difficult decisions that behave like picking, where you say, okay, then a difference in $1 should bias my decision because I don't care. It's equally important to give to hunger and to cancer. Or if the decision is so important to you that you consider it an insult, to be affected by $1 when you make that decision. So that's one response. And the other is that if this would have been the case, we would have expected subjects to respond as fast as possible in these trials. And what we see is the opposite, right? These trials are so difficult that they are the longest. So it at least seems as if there is a different mechanism here. That it could be that at the end of we deliberate, and then you cannot make a decision, and then it becomes picking. But we don't have any evidence that this is the case. But it's an excellent point.
Can I ask, in the individual trials, I understand there is no readiness potential in the deliberate, but is there still the notion of the threshold?
Okay, so I'll get to the threshold just now. Okay, I'll be there in a second. I also want to show that the motor response itself does not differ between the conditions. So when you look at the lateralized readiness potential, it's exactly the same for a deliberate and arbitrary decision, which is why we think that the lateralized readiness potential is a genuine index of motor preparation, while we think the RP might not be, and I'll explain that in a second. And this takes us exactly to your question, Gili, and to the model by Aaron Sugar. So in our opinion, the model actually would predict this type of pattern of results, because the model says that in the Libet type experiments, because we don't have any other reason to move at a certain time or to select one of two options, there are also some Libet-like, Ariel has done that as well, experiments where you choose if you want to press right or left, or pick, I would say. Then in these types of cases, what drives you are random fluctuations. But in deliberate decisions, we think that there is a different mechanism that determines whether you're going to choose the hunger or the cancer organization. So what we did, and when I say we, it's actually Uri, because I am not a computational neuroscientist and Uri is. So what Uri Maoz did was to create a model to take Aaron Sugar's model and implement it on our case under the assumption that there might be two systems that drive these two types of decisions. One system is the SMA, the supplementary motor area, over which the readiness potential is typically recorded. And that is that would be driven, like in Aaron's case, by random fluctuations. And there is another system, which we don't know which one it was. It could be the ventromedial prefrontal cortex. This is, it would be any value-based region, a decision mechanism that we have. So we called it region X, just to stay completely agnostic about it. And the idea here is that for each one of these systems, we would have a race to threshold between two drift diffusion models, which is basically Aaron's model. One, accumulating, it's not evidence, but activation towards selecting cause 1, and the other towards selecting cause 2, okay? And then the idea would be that if indeed, when we record over CZ, we only record SMA activity. So what we would expect to see is for the noise to build up, the random fluctuations to accumulate when we are making meaningless decisions, but not to accumulate when we are making value-based decisions. And why? So now I know it's a very kind of flashy figure. I apologize for the colors and for the noisiness. But what you see here are different runs of the model, okay? And this is what we would expect to see over the SMA is, so the models of the SMA are in 2 shades of gray, and the models in region X are in, so actually you only see here in green the congruent model. So the DDM model that leads to making a decision that is congruent with your ratings. And what you can see here in the kind of fragmented line is the threshold for decision for region X. So now in each trial, we have the 2 models running. And if this is a deliberate decision, then what we do computationally is to set the boundaries, kind of the threshold for the SMA model at infinity, so it never gets there. And then in each trial, there comes a point, it's annoying that I cannot use my mouse, but there comes a point where the green kind of run crosses the threshold. And in the red arrows, you can see where does the model in the SMA is, where is the model in the SMA when the threshold was crossed for the region X. So basically, as you can see here, although all the runs of the model in region X end at the threshold, so they all cross the threshold, otherwise there wouldn't have been a decision, right? So they all end at the same point. When we look at what happens in the model that tries to represent what's going on in the SMA, that model stops at a random point, wherever it is, because the decision in deliberate decisions is not set by whatever is going on in the SMA. It is set by whatever is going on in the value-based mechanism. So the prediction here would be that because the model stops at a random point, the SMA model stops at a random point, there will be no accumulation, artificial accumulation of noise. For the peaking condition, we always stop when noise is at its peak, so it accumulates. But for the choosing condition, every time we stop at a different point, because noise is not driving the decision. What's driving the decision is the value-based mechanism.
Okay, we have to, yeah, time is running out. Unfortunately.
Oh, sorry. Okay, and I have to go. Okay, so I'll just finish. I'm so sorry. So what we did was to find the parameters, feed the parameters to subjects' behavior, and then get, oh, sorry, I don't know what happened now. Okay, so let me just explain to you. So, and then get a prediction from the model about how the EEG should look like for deliberate and arbitrary decisions. And what we've seen is exactly the pattern that we found. So if you assume that what you record in CZ is only noise, then you would expect to get an accumulation of signal for picking and nothing for choosing, which is indeed what we found. So what we think our results show is A, that the readiness potential does not generalize from picking to choosing. And we hold that choosing are more interesting for free will and the debate over free will than picking. And B, that our results are compatible with a model which assumes that the RP is not a genuine marker of unconscious decision, but rather the result of the accumulation of fluctuations. And I apologize if I was so enthusiastic that I didn't pay attention to the time. So I hope that you were able to understand